How's everybody doing? Good. I got the after lunch lull, so let's see if I can keep you guys entertained or fixated a bit. All right, it looks better here than it does on my laptop, so I'm gonna follow. So today's lesson is actually going to be a little bit interactive. We're going to be covering PyTorch, but we're going to start off with some very, very basic things, just kind of find out what's going on under the hood. And then from there, we're going to dive deeper into some other topics, like CNNs, transfer learning, and then at the end, especially if we have enough time, we'll actually cover some RNNs. Right? So I want everyone to please go to this website, collab.research.google.com, because you're going to basically be running the exact same things I do, right? A 90-minute tutorial where you just watch me, you guys will fall asleep. So if you guys follow along, you guys could actually keep this at the end, or you could pull from my GitHub by the time actually by tomorrow I'll have everything nice and ready. Right now this is just sort of the hands-on part, but I'll put up solutions, etc. if you guys want to go. So collab.research.google.com. So you need to have a Google account, but I'm guessing 99.999% of you do. So we're good. When you go on there, you're going to see some sort of web that looks kind of like this. Let me see if I can make this smaller. Oh, that's fine. That's quite big. There we go. So raise your hand if you're at the screen here. All right, let's give it a couple seconds. For those of you who are already there, type in this, https://github.com/Robert-Alvarez. So it's github.com, obviously, but you have to put the HTTPS. And then my username at GitHub, which is Robert-Alvarez. Once you've got that, if you hit tab, it should generate, you might get this. This happens whenever there's a lot of tutorials going on. It thinks everyone's trying to hit the GitHub API. So just authorize it if you get that error message, and it's literally PyTorch tutorial handle. If you have any questions, please feel free to raise your hand. And the first 5 minutes, we're going to start getting set up. So, how did I get the what? The thing here? Yeah. If it doesn't pop up automatically, go to File, Open. If you hit Tab, it should automatically populate the repository. Like here, it'll have actually some of my other repositories, but
you may have to sign into your GitHub account.
You might have to sign into your GitHub account.
So how do I get it? Because now it's just not doing anything. Because I closed it. Like if I hit Tab, it just does it.
Oh, then see if you could have to log into your GitHub account. Yeah. Yeah, or try to put connect or. Out of curiosity, how many here are students at a university here? So I don't live here anymore, but I'm actually from Miami. So I went to FIU. Okay. Got my 2 bachelors and my master's there. So.
Did you go to high school in Miami?
Yeah, I did actually. I went to Sunset.
Okay.
Yeah. So I wasn't born here, but I pretty much like I moved here when I was 5 years old. So. I miss Miami. I actually came literally just for this conference and to see my family, and I'm going to be in Miami less than 24 hours. It's actually pretty brutal in terms of flight, but well, that's too. I came for the conference and to see my family. All right. And most of you here, right? Just click on this guy. PyTorch tutorial hands-on. Should load this web page. I'm going to move this because I prefer standing, and this thing makes me feel like I have to sit. Take it. If you want to take it. I don't want to stand. I don't want to sit. So, wow, man, this thing is really Apologize for the, there we go. That's starting to look a little better. I'm pretty much zoomed out all the way I can. All right. Raise your hands when you guys are here, or I could at least see this. A little less, starting to get a bit more. All right. We're almost close. We're pretty close to starting, though. For those who are already here, though, so there's going to be a difference between installing PyTorch locally and doing this on Colab, right? So if I had asked you to do this all locally, you'd have to go through the conda install or install from source. Make sure, and you guys would all have to pull from my GitHub repo. It's just going to take too long. So it's a lot faster to go to here. Once we are connected, click on runtime, change runtime type, and see here that there's now the option for a GPU. Right, so one of the things that we want to use PyTorch for is the fact that it's GPU accelerated. So we don't have to use the CPU for computation. We can actually use some of the cores from the graphical processing unit. And Google gives this to us for free.
How do you get that?
So I'm going to hit cancel.
Yeah.
Unfortunately, on my screen, it looks quite small. You go to runtime, change runtime type, and then add hardware accelerator, add GPU, not TPU. All right, do that, hit save. I'm going to first see if I can change the preferences here. This is really, let's see if this is better. It's like,
I use the built-in.
there we go. Oh, the built-in retina?
Yeah, they'll map to your screen. See if that's any better.
Yeah, that might be the best, because now I can actually bring this up.
Yeah, control plus.
Yeah.
It looks pretty broken.
Looks pretty crappy here. All right, I'm going to go back to that previous one. Apologize for all the issues. Sometimes it's best to go through these headaches at first and then deal with things later. There we go. That's better, right? All right. A little bit more? Oh, okay, yeah. So, what did I say? Change? Go to runtime, change runtime type, and make sure that GPU on the hardware accelerator is selected. All right, hit save. And then, as I was mentioning, to install PyTorch on Google, it actually has to deal with this small little command. It's just much easier to cut and paste and try to do the whole conda install. Google actually provides that for you whenever you try to import Torch. So just run that very first line. If you haven't run anything, you can just hit unclick the reset runtime, but if you don't, it's really not a big deal. It's going to take a half a second extra. All right, that one's done. And then if you click on the next line, this fixes an issue that I have with PIL that doesn't work on Google Colab. So if you don't run this, you're going to get an error when we're going to the transfer learning part. So make sure you run both these lines.
Do you wait till the first box doesn't have the square?
It does it just like Jupyter Notebook. It does it in series. Ooh,
Okay.
I just realized I'm going to restart mine just so that you don't have to restart yours. I realized that mine actually was still from my previous connection. All right. So, if you guys wanted to install PyTorch using Conda, you go to that little thing right there on your local browser, on your local machine. But we don't have to do that, right? So this is before if you guys want to play with this later on. If you have a MacBook, you can't use the GPU accelerator unless you install from source and you have a GPU. So most of the time, if you install locally, you're only going to be using the CPU. Well, for what we're going to be doing today, right, as all of you, this is a PyData conference, this is a Python conference. We're going to be importing some of the usual suspects and the things that we're going to be having to do generally, right? Import ROS, some requests, some zip files, some things that do handle images, obviously NumPy and pandas. But here's the good stuff, right? So this is the reason you guys are all here. So PyTorch gets, the library is called Torch instead. That's the original name from it. So it's import torch and then imports.nn, which is a neural net module as NN, right? And then we're going to be importing autograd, which is the backpropagation automatic differentiation or automatic gradient. Some other the functionals that I'll start talking about in a bit more context. And then from Torch Vision, so like vision, like computer vision packages. Right, and then kind of the usual stuff. Right, matplotlib inline. Right? And then all of the data lives here. Right? This is a link to a Dropbox that will automatically download all of the data that we need today. Right? And that should be fairly quickly because we're doing a network-to-network transfer instead of from network down to your laptop. All right, this might take a little bit longer for you. I already have this downloaded. All right, anyone still not here? Anyone not being able to follow along? The which one? For the github.com/Robert-Alvarez. So it's my name, Robert-Alvarez, not underscore. All right. Everyone good to go? Awesome. All right, so now we could actually get started. We've got all the data locally. We've installed PyTorch. We've got all of the libraries imported. So now we're going to start. So what is PyTorch, right? So PyTorch does two things, right? It's a replacement for NumPy using GPUs, which in my much longer version of this tutorial, we would cover in a little bit more in depth. And then the other one is PyTorch is a nice deep learning, like a flexible deep learning platform. We're using Python, obviously. So we're going to be focusing on the second one, which I guess is the reason why you guys are here. You don't care how to use NumPy on a GPU. So we'll skip that part, although if you guys want the longer version of it, it'll be posted on my GitHub tomorrow. I just didn't want it to clash. I didn't want you to be clicking on the wrong link. Right? But to talk about PyTorch, we need to talking about tensors. Right? So what are tensors? Right? We all know what a matrix is. We all know what an image is. And, well, a matrix is just a sort of a 2D tensor. And then an image is really three matrices stacked on top of each other. You've got, especially if it's a color image, so you've got the typical the red matrix, the green matrix, and the blue matrix. This is what we call an RGB image. And when you stack those three together, you get a 3D tensor. And that is what we call a tensor. And tensors can actually go as many dimensions as we want. A 1D tensor is a vector. A 2D tensor is a matrix. 3D tensor is an image. 4D, et cetera, et cetera, et cetera. Right, so we've got this typical picture of Grumpy Cat. Grumpy Cat, although when you see it on your screen, it looks like one single image, but really behind the scenes there are actually three different matrices telling you the color coordination of each of these. And we're going to need to be doing a lot of manipulations on these because we'll see that images in particular do really well in neural nets because we're going to try to find patterns in them. And we're going to be, since these are all tensors, input's going to be a tensor, and then we can do a lot of the manipulation behind the scenes using that as well. Right? So here would be sort of an example of the red matrix, the green matrix, and then the blue matrix in the back. Right? And here's a nice little visualization of what these tensors look like in several different dimensions. Right? As I explained before, 1D tensor is just a vector, 2D tensor is a matrix, the 3D tensor is a cube, right? But then you can keep on extrapolating, so on and so forth. So a 4D tensor is really as a vector of these cubes, et cetera, et cetera, et cetera. Right? You have to be very careful when we import really large tensors, though, because they take up a lot of memory. So you'll see, especially when we do some of these image classification tasks, we actually really downsize the quality of the image quite dramatically, because otherwise we could run into serious computational issues or memory issues. Right? So, starting off with neural nets. Right? You guys are all familiar or know or have heard of a neural net, right? So, neural net, and this is basically the most common one. This is what we call a perceptron. So you've got some inputs, right? So these are the inputs being fed. These inputs each have a specific weight. So for example, do we want to weight this input stronger to make sure that whether we activate this neuron, right? So this is, think of it as the typical single neuron that's coming up with some attribute values, right? So, did I burn myself on the oven, right? So I've got some sort of sensory input. Once it crosses some threshold, the neuron activates, and I get a reaction out, right? So this is the very basic thing. And now if we stack these many, many on top of each other and wide, we start getting what is called a neural net, right? So this is just the very basic one. And what it really is just linear regression. Right? It's just a linear regression. You take all of these inputs, you multiply them with weights, sum them up, and find out if you're above some threshold or not, if you want to talk about activation or not, but in general, it's just linear regression. Right? But we can have more of these, but we also want to find out sometimes if we've been activated or not, right? So if in the slide I showed you before, it was just a linear regression, it summed up the weights times the input, and it just left that number out. But there are times where we want to say, hey, did we cross some sort of threshold? For example, are we positive now or are we negative? And if so, then we can use some sort of other like squashing function or so-called activation function to say, hey, now that this input is above 0, let's set it to be 1 going forward so that we've activated the neuron. If we didn't, if it's less than 0, we just say, oh, now just flatten it into be exclusively 0, and it didn't get activated. Right? So this is very similar how we think the brain works, which is why it's called neural nets, but I don't think that's the case. But it does help right in terms of doing classification functions. So if you're looking at like a fraud detection algorithm, we really wanted to, we're going to take in a whole bunch of inputs, pass it through our net, and determine whether or not this person committed fraud or not. So it's going to be a 0 or 1. So ultimately, we're going to try to pass it through this neural net and say, hey, once we squash it, where is this boundary to determine whether or not we're 1 or 0, right? If we commit fraud or not. But the way that we've done this is, right, so we need to be able to train this, right? So we used to initialize the weights at some sort of value and propagate through this net or through this perceptron and determine whether or not we got close to what the training data tells us, right? We're always going to be looking at training data. We don't create a neural net that automatically happens to have the right weights, right? So we start off with some training data. We pass it through this neural net. We do a forward pass saying, hey, we're going to initialize the weights at 0. We're going to pass it through this net. We're going to activate all of these things. And then we're going to look at the output. Is the output what we expected? No. Well, how far off were we? And let's propagate back and then change that so that we can continue to update those weights to get closer and closer to the true output. And we'll go into much more detail about that later. Right, so we're going to be computing, right, to initialize the weight for each of the samples, right, compute the output, calculate the error, and then update the weights. And we update the weights by using the new weight is the old weight plus some gradient or some learning rate times the gradient of the error. Right. So, going back to this, right? So this is kind of how we fit a model, right? With the same way. We've got our inputs, our outputs, our learned weights. And the algorithm is the same. We're now just going to be a little bit more mathematical about this, right? So we're going to have some sort of loss function, right? Whether it's cross-entropy loss or mean squared error loss. And then we want to update the weights using backpropagation. So in this case here, this is a mean squared error loss. So we say, hey, what is the difference between my predicted value and my actual value? Square that difference, and say we want to minimize that as much as possible. This is sort of like what you're minimizing in ordinary linear regression as well, or in ordinary least squares regression. And here we've sort of slightly changed the notation around. It's a minus sign, but it's got the learning rate there. So you want to modify this learning rate. One of the things that you can modify in a neural net is that learning rate. If you make it too big, you might actually overjump the next step where you're supposed to be going. So let's start off with a basic example. If you click on that little line here, it should actually automatically populate the cells. What we're going to do is create the most complicated adding machine we can, right? So here is the very first time we're writing PyTorch code, right? So our model, right, is going to get neural net sequential. So basically a neural net sequential is going to be saying, hey, do these things in sequence, right? Pretty straightforward. And we're going to do something very simple. We're going to take the two inputs, right? So we're going to take two numbers, and we're going to get one output. And it's going to randomize the weights, and we want to find out how long will it take for it to train where they can add two numbers or not, right? We know we can do this. Kids can do this. This is actually fairly slow to do. Well, you'll see how long it takes. So the optimizer, we're going to be using the atom, which is sort of like a variation on stochastic gradient descent. And our criterion, our loss criterion, is the mean squared error loss, right? We want to find out what is the square difference between our predicted value and our actual value. Right? And if you print model, it actually tells you what are the layers of each neural net. Remember, we're doing this very, very basic. We said in number of features, out features, we don't want to set the bias to be true. So basically, we could have added a bias term. This is the same thing as adding a constant in linear regression. But we're going to avoid that for now, just because we know it's not going to be necessary. So we're going to train this model. Right, we're going to go through 10,000 samples. We're going to create a random number, right? So we're going to generate random numbers on the interval 0 to 4. We're going to add them together, and that's going to be our target. Right? That's what you see here. Our data is the actual variable x that we generated. And then our target is just going to be, well, x0 plus x1. Very, very easy, but it's a nice little illustration because it abstracts the way of what we're actually trying to program. It just focuses on the code. So the output's going to be, well, what is the model for that data? And then the loss is going to be the output and the target. And then we want to append the loss. And this optimizer, this zero gradient, so every time I do a forward pass through the neural net, a backward pass to the neural net, I calculate the gradient, and then I need to zero out that gradient so that it loses it from memory and does the forward pass again, sort of from scratch with the new updated weights, and goes back. Right, so we got the loss dot backward. So this is where if we had covered sort of the NumPy GPU version, you would have covered a little bit more of this topic, but pretty much the optimizer needs to get a gradient zeroed out, then we do the backward step to calculate that gradient, and then we do the step forward. That's all we're doing here. So if you press play, it should be fairly quick. Ran. And now this is just a plot of this. So our very, very slow adding machine took almost 2,000 samples for it to finally figure out that it was trying what the weights were supposed to be for each of those calculations. So we started off with some random numbers, calculated a gradient. That gradient was off. Did it again, right? Updated that gradient. Did it again and again and again. It took almost 2,000 samples for it to realize that the weights should have just been 1. But this is what it's doing no matter the task, right? We could have been doing this in image recognition. We could have been doing this in like a language model, right? So I'm abstracting away all of that and just saying, hey, what we're trying to do is just the backward path. Is the update of the weights. And what did I do here? And this is the model outputted, right? So you've got it's hard to see on the overlapping. There's actually the red dots, which are the predictions, and the blue line, which is the actual. So we generated data on 0, 4. That's where we had our training data, right? As with everything that we're going to be doing in machine learning, we have our training data, and then we have things that that are outside of our training data, our sort of validation set. So we want to say, hey, yeah, we've got our accuracy rate here, and we're doing well, but we know that this is sort of a contrived model, right? But we could start doing a little bit of different things. We could start adding nonlinear activation functions, which we'll see in just a second, to see how that actually affects And particularly, you'll see that it starts to get the data right, the training data right, but it starts to then perform differently outside of that set because it thinks it's got some nonlinear qualities to it, although it was able to get rectified down that path. Right? So this is a representation of a feed-forward neural net, right? So we've got our inputs here. This is what we've been doing all along. Passing it to our first layer. So everything between A1 and A5, or sorry, 2 and 5 are our hidden layers. This is our input layer, and 6 is our output layer. And these biases were what happens when you set bias equals to true. So this is just sort of saying, hey, we should have maybe some activation boost to your signal. So for every single one of these inputs, I pass these through. Remember, every single one of these blue lines has a weight associated to it. So we've got weights here, weights here, weights here, weights here, and weights there at the end. So for every single time we go forward, we multiply all these weights, and when we come back, we say, hey, how much were we off by there at the output? Update those weights. Then how much were we off by between these two layers? Update that layer of weights, right, using the ones that you had from the output. So this is what we call a feed-forward backpropagation net. We're going to be going forward through the neural net. We find out what that error is, and then we go back. The hidden layer, well, that's what we did in the sequential. So if I go back here. So the input layer and the output layer are always defined, right? The first layer of the neural net tells you how big your input is. And then the last layer of your hidden layer tells you how big the output should be. So in this case, when we said here, I'm getting two things as an input because this is the first layer, the first hidden layer. So how many things come before me? That's my input size. And since it's also the last layer, the last hidden layer, it should tell me how many things I need to output. Okay. All right. So there are many different types of activation functions, and PyTorch has even more than these. I kind of mentioned the most common ones. That you've got your sigmoid, right? Your ReLU is the most common one, right? So basically, ReLU just says, if you're positive, give me your value back. If you're negative, you get squashed to 0. Right? Leaky ReLU has a little bit of sort of leakage on the negative side, and then the sigmoid is just a standard sigmoidal curve or logistic function, right? But let's see what happens when we start using these, right? Because if I stacked 30 layers of nn.linear without any nonlinear activation function, I have just done linear regression. There's nothing different, right? It's just now a whole bunch of different weights. I could have combined all of those weights together and had a different weight, and it's just linear regression. But the interesting thing happens when we start using nonlinear weights. And neural nets are Turing complete. But sorry, I don't want to make sure I use the right word. They can approximate any function. That's the word, right? So since they can approximate any function, they have to be able to do nonlinear functions as well. So that's where this sort of play comes into effect. And you'll see some of the other things that we can do specifically for image as we get that farther down the left. So again, we have now just added more complexity to our adding machine. Nothing different here. We start off with our layer. So we start off with 2 nodes, right? So our input's still the same. We're going to take in those 2 numbers. And then we're going to say, hey, give me those 2 numbers and then output 20 with different weights associated for each. Right? So we go from 2 in the beginning. So in this case of this representation, we would go from 2 to 20 on the first layer. And then take that output, pass it through a sigmoid. It does not take any parameters because it basically gives you the same input as output size. It just says, hey, just pass it through this function. And then again, we're going to say, give me some more linear features, squash it again, more linear features, squash it again. And at the very end, I need to go from the size that I had before, and then 1 being the output that I want out. Right? So I always like to plot this just so you can see exactly what the steps are being done in the neural net. So in that graph that I showed you before, there isn't that representation of the squashing function. So we pass it through a neural net and then say, hey, were these cells activated, or these neurons activated via some sort of squashing function or activation function? Yes, pass them on to the next one, et cetera, et cetera. So we run this again. Should take me fairly quick. And because of the nonlinearity aspect, remember before when we just had linear, it took a little bit less than 2,000 steps for it to finally balance out, but by adding some nonlinearity, we were sort of confusing the model a little bit, right? And then saying, all right, now it's going to take us a little longer. So it took almost 3,000 samples or 4,000 samples to figure out how to add two numbers. So these things are dumb, but they're very efficient. They work very well.
Why was the bias set to true?
In this case, just so you could have set it to false either way. What it would find out is, because it now has to do three weights, right? So if I had bias equals false, it just goes input to the weights. If I have bias equals true, I have a 1 as an input as well, and then, as one of the parameters. And it needs to realize that that weight is 0. So I add an extra weight to my model. I add an extra layer of complexity. But, so we're doing fairly well on the actual place where we have training data, but this is one that doesn't generalize well because what we really have is linear data, but we're trying to approximate it with a nonlinear function. So we're going to be getting off on places where it thinks, oh, from here on out, you must be nonlinear since I'm a nonlinear function. Right? I can sort of rectify you as much as possible where I have the training data. If I had made this wider, same thing would have happened. I would have had it rectified a little bit longer, but I'm still going to start dropping off in the tails. Right? And if you see, this actually looks sigmoidal. I'll go through this one briefly. This is the exact same model, but instead of a sigmoid, I've just passed the ReLU, right? And let me put up my screen brightness because I can't see anything on my screen. We start getting this typical flat and then right. So we start seeing some of the little patterns of what the activation function is doing behind the scenes. Right, and sort of the last basic one before we get into the really fun stuff. Right? Well, it's pretty easy to teach a machine to add two numbers. That's kind of one of the first things we ever did with computers. Can we teach it to draw? Right? And if so, how long does it take it for us to teach it to draw a circle? So what we're trying to make it, for the math folk in here, we're trying to make it give enough approximation to this matrix, right? It's a rotation matrix. Can we, by using a neural net, generate a rotation matrix with giving it enough training data? Right? So,
beyond that one, just moving back, the activation function seems to be doing a lot of the work.
Yeah.
And so those are the standard activation functions. If we were to create a custom activation function to do just about anything, isn't that really where the power of the neural network is? The computation is really done by that.
yeah, but you also have a lot of interactions between these, right? So you can have so there are many different activation functions you can use, and some work better than others, right? So for example, you had like max pooling in CNNs, and now batch norm seems to be the nicer one, the new
I create a
hotness.
new one, a sexy activator, whatever.
Yeah. And so it does do a lot, because the reason why is because that's what gives you that nonlinearity, right? So if there's only so many functions I can generate with ReLUs, right? So like as I was mentioning before, a neural net can generate any type of function as long as I have the right activations. But without the right activations, I'm limiting myself, right? It's basically having one arm tied behind your back, right? Unless you get the right activation function, it becomes really difficult to get the solution to the problem at hand.
So are you reducing the problem to the basest activation function? Or
So I would start off with something basic, right? To see what is it that it's getting wrong, right? In image tasks, there's a whole different thing altogether, but in image tags, you usually want to do some sort of convolution, some sort of max pooling, batch norm, many layers of convolutions, right, to get things at different sizes, at different scales, and actually go into a little bit of detail on that later on. But yeah, you are right. Without the activation function, this is just linear regression, and I could only get lines out.
Yeah.
So that it is the workhorse. Yeah. This very first part is just basically boilerplate code of plotting and training a model, right? So I just kind of wrote it all in a function, so you can skip it for now. And then here it is, right? So this is the first time we're actually declaring a class in PyTorch, right? So before I just said, hey, the model gets NN.sequential. And that's very basic for a simple model. 99% of the time, you're going to be doing things that an NN.sequential can't handle, like convolutions it can't handle. So you'll have to start creating your own classes. So class, rotations, or whatever, my neural net, whatever it is that you would like to call it. You pass it the NN.module, and it inherits from the superclass. Right? So it's going to inherit its initialization from rotations.self. And then I need to declare each of the layers here, right? So I've got self.layer1 is nn.sequential. I know that I said nn.sequential is basic, but I wanted to show you what happened. Like, this is now the very first time. So I'm taking the very basic one and defining it as a class as we then change the complexity of it. So layer 1 is a sequential. You've got a linear layer. It's got one input. Remember, I'm only passing it theta, and I want to get it the 4 different rotations, well, the 4 things on the matrix. So one layer, the number of nodes that I'm going to be trying out. Then I'm going to squash it using a nonlinear activation, because otherwise I couldn't generate a circle. And then again, pass it to a linear and give me back true output. And then this is the forward layer. So this is something you have to define in PyTorch. So once I've defined my layer itself, I must define the forward path. How is it that it's going through the forward steps? And then one of the nice things about PyTorch is that I don't have to define the backpropagation. It already knows what are the gradients associated with this forward path, so I don't need to declare that. But in this case, it's very straightforward. We're going to be slowly increasing in complexity. Our out is going to be this self.layer1. So this layer 1 is this entire node, like this entire sequence of things. So pass it through here in a forward step, and then it automatically knows what the gradient is. Then I'm going to define my model, right? It's just going to be the class of rotations. My optimizer is not changing. My criterion is not changing. And then I'm going to train it through this. I should have told you to run this while I was talking. I should have started running this while I was talking. It actually takes a little bit longer. It takes a couple minutes. Oh, sorry, not a couple minutes. Go through like 30 seconds or so. Yeah.
What is the criterion when you say MSE? I mean, it's a circle that we're trying to plot, right? So how would be the MSE calculated?
The difference between the point. So remember, I take in a theta, and I generate an xy, right? X equals cosine theta, y equals sine theta. And then I find out, well, given the real theta and these generated ones from the weights, how far off am I from that in a sort of Euclidean sense?
So it's essentially the Euclidean distance.
The Euclidean distance is my mean squared error loss. Good question, though. I have to think about it for a second. And this does take longer because remember, we're not adding 2 numbers. You'll see a lot of messiness in the loss function, but you'll see it starts to get pretty good. And you'll notice that in the next line, I start teasing, like, will a deeper network work better? And this is where we go into the topic of, if I add more layers, I'm adding more complexity in terms of computation, but I'm able to get a lot of that fine nuance that I just don't get with a lesser amount of layers.
You define the layers in the class, and then you, in the model object, you call the class and you just define the optimizer and the other parameters.
Mm-hmm. When this is done running, I'm actually going to run the next one as well, so that while I start talking through the information, you'll see how much better it gets just by adding a few more layers, right? So this is just, here we go. We got a linear, a sigmoid, back to a linear. If we then chain these, in similar ways, or we could have added different types of activations. So here we go. Let me first run this one. You guys can run it as well. But, well, I think that's actually, there we go. Yeah. So this is my loss function. Remember before when we had the adding the two numbers, it was just pretty much dropped off right away? Well, now I'm trying to get few things correct, and I start notice that while I do okay, this is actually me trying to trace out a path on there. You had a question? Because otherwise I keep information from the previous gradient, and then now I'm at a new location. I don't want to have information about the gradient at a previous location where I was at, and I'll have a little visual of like how it's really going down this gradient descent. And I don't want to have information about a gradient at a position that is not where I'm at. Is really the gist of it. So we only generated our random numbers. Our training data only comes from 0 to 2 pi. But it's actually able to do, not great, but you start seeing that it's able to start extrapolating elsewhere, right? So this is kind of the thing. We always use it on our training data no matter what we're looking at, and then we basically say, how well is it doing outside of that? Right? And if I go into a much deeper network, I may be actually able to get as many rotations as I want, only feeding it data between 0 and 2 pi. Right? But then obviously the computation complexity increases dramatically. But pretty nice that I can actually generate rotation matrices using neural nets.
So this one, on your functions, you have CUDA equals false. So are we...
Do I have CUDA equal? Did I put where? Sorry, I'm trying to find. Oh, yeah, I must have passed it from before. This is why it's going so slow. If you change that to true, this should actually run much faster. I was wondering, I was like, why is it so slow? I must have missed that elsewhere. In the training function? Yeah. It's in the, so when I define like rotations, in the, like here are the helper functions, one of them has CUDA is false. CUDA is the GPU, it should be true.
You have them plot circles too.
Yeah. Well, the plot circles, I think it just needs to go from CUDA to NumPy for it to plot. So I think that one is correct. But we're almost done, and then everywhere else it definitely has CUDA. And you'll see a dramatic increase in speed, especially when we go into sort of the CNNs where you're like, wait, I do 60,000 images in the same amount of time that I do in half the time or a quarter of the time that I do rotation.
I could look at the matplotlib code, but just checking again there, those circles, that's when we only have training data from like 0 to 2 pi is your left circle. And then
Yeah. So this is my actual, this is where I generated data from, 0 to 2 pi. And now with a deeper neural net, I'm actually able to get really good precision from 2 pi to 4 pi, even though I never fed any of that information. Right? I start doing terrible at 4 pi to 6 pi. But if I go deeper and deeper and deeper, I could start generating unit circles no matter what theta gets passed to me without even having to do obviously some conversion to bring it back down to 0 to 2 pi. So going back to your question, I don't know your name obviously, but you had asked, like, why do I want to zero out the gradient? So I'll first talk about this graph, and then I'll talk about what the paragraph on top of it is. So every time we start off a neural net, we initialize some weights. This heat map you see here, this sort of contour map, is the sort of space in which my function lives. It's going to have its valleys, it's going to have its peaks, and I'm trying to find the minimum, right? We're always trying to find the minimum of our function, which is where we're going to have the least amount of loss, the highest precision, et cetera, et cetera, et cetera. But I do that sort of doing, I don't want to say a random walk, but it's by a gradient descent, right? So I start off here, I find out where is the steepest part where I'm standing. So you could think of it like if you've ever been climbing, you're like, okay, this is steep, I don't want to go that way. Well, this thing says, yes, I do want to go that way, but in the opposite direction, because it's going to get me lower as fast as possible. So then I start jumping around here, but the thing is, once I was here, this piece has a gradient that corresponds to that level. So once I go here, I need to forget the gradient there and say, okay, now I'm at a new spot. What is my gradient here? Where should I go next? And then I do this sort of, looks like a random walk, but it's not. And until ultimately I find my minimum. But as you guys all know, there are many places where we can find local minima and not the global minima. So one of the things that we talk about this Bayesian approaches is that you would train multiple models at once with different initializations to then say, let's run a whole bunch of these with different parameters and find out where is the one, instead of running the same model over and over and potentially getting to the same local optima every single time. Train them with different randomizations so that I could have started here and maybe gone to this minima instead of that minima.
So is that like shortest path but on like a 3D like space?
It's not shortest path, but it's trying to find the steepest descent.
Steepest descent.
But the steepest descent, and if I end up going over here, now once I've reached this valley, I can't get out of there anymore because everywhere, the steepest place is where I'm already at. Well, the minimum is where I'm already at. Oh, this is from a different image. This is basically your features, right? So the two features and then your loss function. Right.
But these say they're all like multiple features, right? No.
Yeah, so it's hard to draw in 4D or 5D. So. So in this case, we would say, hey, here are two features. This is what the contour, well, what our loss function looks like as a contour plot. Let's try to find out the minimum as a surface plot, sorry. Right. Sort of jumping quickly, we went from adding numbers, drawing circles to go straight to image recognition. So this is a fairly big jump. But first we're going to talk about image recognition. Right? And we're going to do this because in PyTorch you can already download like so-called famous models, right? You can download ResNet, you can have it be pre-trained, you can download CFAR, which is the one that we're going to look at first. But to do image recognition, we really are going to be passing it through a similar neural net. Right? It's not going to be the typical hidden layer like we saw above where it was just weights, because we need to do a few different types of manipulations to them. We're going to do convolutions. So this image here of this car, right, and if you notice it's stacked because it's an RGB, it's a tensor. This convolution starts looking at it, in the very first layer, convolutions start looking for lines. Right? Whether it's straight lines or diagonal lines, it really just starts looking for lines. And you're like, okay, if I only have a one-layer neural net, the most I could kind of do is, one-layer convolution, the most I could probably do is start trying to find things that look like lines or are jagged. Right? So this is why a one-layer net works fairly well with MNIST, the handwriting data set. It's just lines. But as I go deeper, right, so this pooling is going to start getting me things at different zoom-in rates, right? So at different various levels of magnification, right? So this max pooling might give me a zoom in on an ear or on a tire, whatever. Then I do more convolution, giving me nonlinear features, and I'll show you. There's a great article called "Visualizing and Understanding Convolutional Nets" or Convolutional Neural Nets that has a great image of what each layer in the convolution does. And first layer is always basic lines. Second layer starts getting a little bit more nonlinear. Third, fourth, fifth layer, you actually start to resemble things like dogs, humans, etc. So we do the hidden layer part, then we usually flatten this out to a fully connected path, and then we pass it through an activation function to determine what is the most likely class, right? So we do a softmax, which is basically multivariate, like logistic regression. So it's a softmax. But for here, this is just how one would download the data set. So we're going to transform the data. We're just going to first scale it so that it gets it all centered. But our training set is going to come from the CFAR10 data set. It's going to put it in a specific folder. This is all of the commands. You want it to train it. You want to download it if you don't have it. And you want to make sure that you transform it using the transform that we just described. This loads it. And then the same thing with the test set. We're going to download the test set, but we're not going to train it, right? Because that's the whole point of having a test set, is to see how well it responds. And here are the 10. The CFAR 10 is, I think, Canadian Institute for Advanced Research or something like that. And it just had 10 classes, and these are the 10 classes. So this is just getting us to see what are the images in there. So ship, plane, I have no idea. Is this a frog or a bird? Because these are the classes, right? It's either cat, bird, deer, dog, frog, horse.
Frog? That's green.
Let's find out. Well, I guess we could find out what the true values are right here. It's a bird. All right. It's hard to tell on the resolution here. On my laptop, it's a little bit better, but it's small as well. So we're going to create the exact same thing that we did for CFAR. So we could download it, etc. And I'm going to say, well, let's not download it. Let's just literally create it as we would from scratch. So we're going to pass it through a convolutional layer. Here are the input sizes. We're going to max pool it. So we're going to do a 2x2 max pooling, which is going to zoom in on certain features and get things at different levels of magnification. Pass it through a second convolutional layer, and then pass it through a fully connected layer, and then we are then going to be doing the forward pass is a little different because the forward pass is what starts to do the activation, right? So I pass the convolution through a ReLU, and then do the max pooling, this is where I said it's going to get a little bit more complicated, but we will have one that's hands-on that I will be more than happy to guide you. And then take the second convolution. Again, once you go through the convolution, do the ReLU, and do the max pooling. There's two ways to do reshape. The npy.reshape is .view or .reshape. So I put both in here so that you guys actually see what it does. And it says we're going to reshape it to be this size, which is the size of the pixels, size of the images. And then we're going to say, all right, pass it through the living layer, do a ReLU activation, pass it through the second fully connected layer, do a ReLU activation, and then just output the information out, and then return X. So could you repeat the question?
If I'm switching between using the CPU backend versus the CUDA backend, do I have to worry about how I declare either models or tensors?
So the thing is, if your tensor is defined in your GPU, you need to transfer it to the CPU. And there is a toCPU function, like a dot method that's toCPU that handles that for you. Yeah. Basically. There's a .2 NumPy tensor, there's a .2 GPU. Again, the longer version of this tutorial covers a little bit of that. And you can get it from my GitHub, actually. All the slides are there. It's just, for 90 minutes, it's hard to cram in all of that. So let's run this guy here. Create our so-called ImageNet. And we're going to just pass this through three epochs because it actually takes quite a little bit of time. But we'll see. We pass it through 3 times. This is a very basic sort of classification or neural net, right? We had 2 convolutions followed by max pooling, ReLU activation, connected layer, and then we output. The more common ones are ResNet 34 and ResNet 50. Those are 34 and 50 layer neural nets. This is just one that had 2. Right?
Quick question about the post-connected layers that are after the convolutional map. I've seen a lot of different uses of the FC layers and a lot of different algorithms. Some will, when you're doing a multi-layer computation, some will only have 1, some will have 2, 3, 4. I have never been able to see any rhyme or reason.
I'm with you on that. It's very frustrating because really it's just how hard, if you start looking through the convolutions, if you think you have enough convolutions, you might need to pass it through a few nonlinear, fully connected layers to start getting a little bit more of the nuance instead of trying to capture images. So it's just sort of a fine-tuning of the weight, which is what we kind of do in transfer learning. So there is no rhyme or reason, but we just know it works, so we continue using that method. It's not the best answer, but I know sometimes you'll have 1, sometimes you'll have 3. In transfer learning, we just chop off 2 and insert new ones. But the thing is that once your convolutional layers are trained, you don't need to train them again. Right? They're already captured all the things you need. You just now need to fine-tune the very last piece. And that fine-tuning, depending on the complexity of it, might require more fully connected layers. We go through 3 passes, and then we're going to check to see how this does. Right? So we actually created CFAR 10. Right? I just showed you the code. We're then going to go into a little bit of transfer learning, and we're going to have you guys code one yourselves, and I'm happy to walk around and help you guys out. I just wanted to see how this does. There are 10 types of classes, right? The ship, cat, bird, whatever, blah. If I randomly guessed a class, I'll get it right 1 in 10 on average. Right? So if our model does better than 10%, we're actually being able to capture something that's in the essence of the data. So anything better than 10% is good. We've done 3 layers, and we want to find out how good this does just by passing it, just by doing 3 little training sets, like 3 little training epochs. Almost done here. There we go. Come on, finish training. All right. So here are the images. Cat, ship, plane, right? So this is the ground truth. Let's look at what our model told us. So we predicted cat. For some reason it thinks the second one is a car, not a ship. And it thinks the ship and then it's plane. So like I said, right, we're able to get these 3 right, but that could have just been pure luck. We said anything over 10% is better than a random guess. So we trained this with 3 epochs. And we got 58% accuracy just by doing 3 simple epochs using this data set. There's 60,000 images total.
Choose the ReLU functions if it's not a linear problem.
Pardon?
If it's not a linear problem, why did you choose the ReLU function?
Well, the ReLU function does give you some nonlinearities, remember? Because if the weight is negative, then...
0.
Well, but if the weight is negative, it flips it. So we always think of the ReLU as being 0 if it's negative, and then just a line if it's not. But if I get a negative weight, I now have different things where some of the negative things get activated or not. Plus, I have my bias term to shift up and down as well. So I do get some nonlinearities.
I have a question.
Mm-hmm.
So I'm running same code, but I have right answer cat, shape, plane.
Oh, it's a random image generator. It pulls images randomly.
So we get the same image. Same image.
Oh, then it's just the exact same. Wait, is it like if you do it again, you get the same images, or
I mean, same image with zeros.
if you run it one more time, do you get the exact same images? It should just be sort of the pseudo random number in the back. Yeah, might be the seed. All right, so this is a sort of rapid fire tutorial, right?
Sorry, I'm new to the machine, right? I'm not sure, like, what is the convolution function do on the image? Like, why would we have to do that?
So convolution function is really just scanning. So basically, imagine putting a matrix or like a box over this image, and you're doing calculations based on some weight that convolution has. To reduce the dimension. You're reducing the dimension, getting things at different features, getting different types of layers out. So convolution is just reducing the dimension via some function that just scans the whole image and reduces its size.
Reduce?
Yeah.
Reduce?
Yeah.
Why would you do that multiple times?
Because you get features at different scales. Right, because if I have a picture of a dog that's quite big, and then I have a feature of a dog that's much smaller because it's in the background, I'm still able to I want to look at things at different features so I can capture what is the dog, regardless of the size of the image or where it is in the image. You want to make sure that you're getting things at different scales. Right?
Clarity?
Pardon?
The goal is the clarity of the picture?
Uh,
What's the goal of
I don't know if it's clarity, you just want to start getting nonlinear features and determine what is the essence of this image at different scales. So I don't know if it's clarity per se, but I know that it's a nice little way to think about it, is the convolutions are giving you things in different scales. So then going quickly into transfer learning. Right, it was one of the nicer things that we've seen in machine learning, right? In the late 90s, someone said, hey, I've already spent all this time training a model. If I'm going from an image task to an image task, why do I need to train the entire thing again from scratch? Why can't I use the sort of hidden layers and then just kind of add a couple little layers at the end to do the fine-tuning of the weights to get the right classes out? So I think ImageNet from Google took well over 24 hours to train using Google-like resources. They had 2,000 different classes. They had millions and millions of images. But once you start getting patterns, these patterns don't change, right? So a circle is still a circle, whether it's a circle on a car wheel or a plane wheel or a ball, right? The image, so we're trying to just capture all of these different things and then say, hey, we want to capture these different features, but now fine-tune it so that you give me the right class at the end. Right? Sort of taking a sidestep really quick, this is from that article that I was mentioning, Visualizing and Understanding Convolutional Neural Nets. This is the third layer. The first layer, like I mentioned, is just lines, right? It's got lines going this way, it's got lines going this way. It can only do linear functions. But by the third layer in a convolutional neural net, it's starting to actually get very complicated patterns. So it's starting to notice these sort of mosaic-like patterns from the images, right? So this was what had activated that. You start getting, the spots on a beetle, right? So it starts generating spots. It starts noticing what is the outlines of humans. I have no idea what, shells, right? It starts recognizing what looks like a billboard or a sign with text in it, so that it can start going through many different layers, right? So ResNet 50 has 50 of these layers, so it starts getting a lot of different complexities, and then since you've got so many different parameters, you start wiggling through the neural net until you get to the right class, hopefully, right? And that's what the whole point of retraining it for. But in transfer learning, going back to that, right, we've got all of these parameters, right? We've got all of these layers that we know capture things that are in images, right? I would say that if you're training your model on like ResNet or sort of like ImageNet, where you have 2,000 different classes of what Google, like, cats, dogs, etc., and then you say, hey, I want to look at this to look at like cells under a microscope, like those sorts of images won't necessarily transfer. That might not be a good transfer learning problem, but if you're going, hey, I want to recognize this to this, and they're sort of in the same vein of something that you would take with a photograph of people or the real world, transfer learning actually helps quite well. So we transfer those parameters over, and then we change the connected layers at the end to fine-tune those weights. So this is frozen for network B. So this is the one that Google did, for example. It says, hey, there's 2,000 classes here as an output. I said, well, I don't want 2,000 classes. I want to determine two different things, which we'll get into in just a second. But I want to take all of the knowledge that it had, because it takes a really long time to train this, because it's slow process. Got to maneuver through the entire landscape using gradient descent. You could get trapped in local minima quite a bit. So it says, hey, no, they've already done the hard part. Let's just do the fine-tuning at the end. So now, by using that, we don't have to have millions of images. I could just have a few hundred and say, hey, now I can determine these sorts of things using a transfer learning model. And it reduces the computational complexity dramatically. Right? So since we're in Miami, we wanted to try to see if we can determine, using a transfer learning, the difference between the two king and queen of food here. We've got the famous Cuban sandwich and the stuffed arepa. Right? Got to pay a little homage to the home city. So I'm actually half Cuban and half Colombian, so these are both things I eat all the time. Right? So this is very similar to what we did for the CFAR. We're going to be doing some sort of data transform. We're going to be loading it from a train set and a validation set. Unfortunately, you could have access to the shell system behind Google Colab. You just have to do the magic, like exclamation point ls, but if this was in your shell terminal, you'd say, hey, what are all in these folders? You'd go to data. There's a train and validation. It has each of those images. There's roughly about 250 total images of each. Okay? Not that much, right? Remember, ImageNet was trained on millions of images, and now we're using 250, and we're going to do pretty darn good. Okay? So what we do here, though, which is a little bit different than I did before, this I want to talk about because these transformations are ways that you add randomness. So if I only have 250 images and I want to make sure that I get, a dog looks like a dog, but if I only have dogs facing to the left, I'll never recognize a dog facing to the right. Right? Just the ImageNet, the neural net will not capture it. I also want to think, hey, how about if I look at it from a different angle? Right? So these transformations here, the resize is standard. You always want it to just be a square. Random affine, so you're basically going to do an affine projection and sort of project it from a top view, in a sense. Then I want to maybe do a horizontal flip and say, hey, change it because I don't want my Cuban sandwich facing left, I want it facing right. Because some people may have taken it that way, and then we obviously do two tensor. So for here, we're actually going to use the ResNet 50. Right, this is going to come. We're going to take the ResNet 50. I'll get into your question in just a second. We're going to take ResNet 50. We're going to download it, use the pre-trained version so that we don't have to touch any of the weights, and we're just going to add a layer at the end. The rest of the layers are frozen, and do fine-tuning to go from those 2,000 classes that Google had to just say, hey, give me an arepa or a Cuban sandwich. Right? Sorry.
Question about the resize, is that always like a downsampling?
It's a downsampling because it just takes too long. The images are huge, right? Especially if you have high-quality images, right? There's no reason to use 1080p to do image recognition. It does it very well on low-res images.
All right.
Yeah. You get what the reason why is that the quality itself isn't the important part. It's the variety, right? So that's why we do the transformations because, 224 by 224 images is probably good enough, right? There's plenty of pixels in there, but I want to make sure that I'm getting the variety of getting top views, light side views. You could even do things like, especially fast.ai has this, where you can add like a sort of light, like as if you had shown light on a specific part of the image. And they've got at least 10 to 15 different transformations that mimic what's really happening with the real world and how we see things, right? There's a difference between looking at a cat from the bottom up and then from the top down. So they've got all these nice little ways to do it, but I just kind of started off with some basic ones, right? Randomly flip it and randomly give me a projection of it.
So you're applying these transformations to the two images that you showed us?
No. Those were just two examples of the many images I have. Yeah.
You can also augment the images.
You can also augment.
Make them fat.
Yeah. Stretch them, yeah. So it's like affine projections.
What if an image that both cat, in this case, what if there is both a cat and a ship? What happens? Does it identify?
You should, that would change the task because there's a difference between saying, hey, what is this image? And then another one, which is tell me what is in this image, which is a slightly different task altogether. So I'm assuming for an image recognition task that we're doing, every image has exactly that thing and nothing else. Right? But if we had done I forgot the name of it called, but sort of a segmentation task. I'm tired. I took a red eye. We want to make sure that it's a different problem altogether. It's a different architecture. Right?
You don't have to sacrifice the quality, right?
Just downsize it because it's easier on computation. All right, so we've got our model, right? So here is where we basically tell it to freeze those parameters, right? I basically say for the parameter in this model that has not been changed, don't require a gradient, meaning that gradient, those parameters are frozen. And then we're going to add a fully connected layer at the very end with a ReLU activation. Right? And then we do our typical stuff, right? Cross entropy loss. This is actually fairly quick because we're doing CUDA now instead of CPU. So right off the bat, we're at 89% accuracy on the validation set, and that's to me the one that I care about. But we do jump up and down. Remember, this is we can modify this by changing the learning rate, by changing the number of epochs. Let's see, I tend to do fairly well. We could have just accidentally started at a good point. Let's see what happens. So I'm not going to save this model, but we could save models. Right? So there are many times where you say, hey, I've got to this level of accuracy. I don't know if doing a few more rounds of training will help. Let me save my model at this stage because I can always undo it by loading the model. There are two ways to load models in PyTorch. This is one of them. And I think sort of the one that's less memory intensive. You can just save the entire model itself, which is model parameters, with sort of like all, but what I'm basically doing here is saving the model weights only. Right, so it's kind of like the difference between pickling and saving to a dictionary.
If we got an error at this section, like what might be the cause of that?
Is it a PIL?
Yeah.
All right, that error is fixed by rerunning the line all the way at the top that says fixes error on Google Colab from earlier version of PIL.
Perfect.
But I didn't expect you guys to read that.
Uninstall.
Yeah, you basically have to restart your kernel. Just an FYI, you have to restart your kernel, run those two lines. Well, actually, run the first three lines, except for the PyTorch installation.
If you do exclamation mark pip install pillow version 4.1.1, that works too.
I don't know. Yeah, I know that I just basically got the latest version, and I know that it worked. Where am I? We're almost done with this, right? Yeah, so this is done. We can save the model. Loading the model when you save it as a dictionary is a little bit different, because if I saved the model just like a pickle type file, I would just load that model, no problem, and it'd be exactly where it left off. But when you save it as a dict, you need to load it by first creating the architecture of the model, saying, hey, here is what my neural net is, how it's defined, what are the layers, and then I'd say, here, pass these weights to it, and no need to train. Yeah.
What happens if it's already has
So it just basically goes from a fully connected layer to there. It's trying to then do the fine tuning at the very end. So sometimes I use the word chops off a layer. Really, it just stacks a layer. The output from the original one, no. Right, because they only care about two classes. So yes, I got all of these different things, all of these different outputs from before, but now I'm going to pass them through more fully connected layers to give me back at the ultimate end. Yeah, as long as you add a layer to the end, right? Yeah. So let's see how our model is performing. I'm not going to load the version that I had already saved. I want to see how this one did at 72% accuracy. So here are some actual test cases. As your question said, are there only those two? No, there's actually more. So here's an arepa that it says 99% confident it was an arepa. 86% confident this is a Cuban sandwich. This is 76% confident it's an arepa. And then 99% confident in arepa. So it actually does arepas really well. And I'll show you the difference between that one and then the model that I had before. So I'm going to load my old model. I guess and you'll see that the actual changes. These are all correct now. So I still got arepa, Cuban, arepa, but with different percentages, right? Because of the weights. I must have hit a different, yeah. Yeah, so this is one where it's a little tough, right? Well, we are in Miami. There's Cuban sandwiches around the corner everywhere. The one that says import pillow, like pip install. And you need to restart your kernel. So it's kind of a twofer. So I'm going to ask you guys a question because I can either keep on talking and show you more examples or make it hands-on because given the fact that this was a 90-minute tutorial and there's supposed to be some Q&A at the end, I can either go briefly into RNNs and show you how RNNs work and then show you like a loaded model, or we want to get hands-on with a CNN.
RNNs?
RNNs. All right, so CNNs from scratch, we're going to spitball together. It's basically building your own, but if you guys pull this from my GitHub tomorrow, you'll have the solutions on there. So let me take a glass of water. So a nice way to sort of familiarize yourself with the RNNs is to start looking at things that like character level generation or language models in general tend to work very well with RNNs. Right? And what we're trying to do with an RNN, or actually with a language model in general, is say, hey, here is this piece of text. The quick brown fox jumped over the lazy. And then our model should be outputting the final part of that. Right? It should be outputting space DOG. But what sets apart an RNN from, well, a vanilla RNN, right? We can get into LSTMs later, but what a vanilla RNN from like a neural net. So they really are neural nets, but where the previous layer feeds into as an input for the current layer. So it's the output of this. So this basically says, here's my input, right, however big it is. Pass this through this model, give me this output, but pass some hidden information about this here, as well as this output into there as well. So this sort of recurs on itself. The reason why there's this little recurring arrow, you can actually unroll this and say, no, for every single input, I'm still going to be using this information going down into my RNN as well. Right? So let's look at this going forward, right? So we're going to be thinking this from a character level generation. It makes the sort of the dimensionality a lot easier to handle. There's only like what, let's say 80 types of characters, right, including uppercase, lowercase. But if we went to words, then we clearly blow up into a much higher dimensional space. So you can think of this as being the word, or the letter corresponding to the first input, which would be T, right? It goes through this model. It has a probability of what the next word is. That information gets passed on to the second. Then it sees the H. It says, well, what's my prediction, right? And it's all this time. It's going through this just like it did the neural net, right? It just has to have it just always has information from the past feeding into it, instead of being from the immediate layer behind it. So that's really one of the key differences between a regular neural net, is that the neural net just says, hey, what happened immediately before this layer? And that's all I care about, because I don't have information that trickles from the past. Right? And that's why they came up with RNNs, is how do we have this information keep on going through from much earlier layers to still feed into my current layer. So how does this P1, this prediction, help with P5? I can't do that with a regular one, so that's why they created RNNs and then some variations of it, LSTMs and GRUs. Right? So LSTM stands for long short-term memory, and GRUs gated recurrent unit. They're quite similar. Their architecture is a little bit different in how they forget information. Okay. And like with any neural net, once you define a forward path, you have to have some sort of way to calculate the backward path, which has the gradient calculation as well. So it's a little bit more involved, so this is just sort of a visualization, but we will forward to the neural net, we go back through the gradients and update each of these weights, and remember these weights are then feeding through the hidden layers as well. So I'll go into the steps here of how this is done. There's obviously going to be a little bit of pre-processing. You want to make sure that you take, so what we're going to be doing here, just to give you a little bit more context of like what the problem is we're trying to solve, is I have text here from Shakespeare, right? And I want to generate text that sounds like Shakespeare. But I need to take his text, and I can't take the whole thing, right, because I'm going to run into memory issues, but I'm going to say I'm going to take chunks of it at a time, because I want to capture a little nuance in paragraphs instead of the whole body of text. Right, so in the nuance, I want to say, hey, I'm going to get like 400 strings. So, all right, this is the typical import for language. This is the entire file length. There's around 10,000 characters in this file. And I'm going to generate a chunk length of 400 characters. So that is going to be my training size. So my training input is going to be 400 characters chosen randomly from Shakespearean text. Right? 400 sequential characters, let me make sure. Right, so here I actually started off with the end of a word, but that's fine because you'll notice here it is literally the play. Like you would see Romeo, you would see Juliet, and then the part that he, she says. One of the beautiful things about this is that it actually starts generating names that are legit from Shakespeare. It'll say, hey, Romeo said this, and it makes 0 sense, but it's still got Romeo. So it's actually quite cool. So this is just sort of the pre-processing, getting things set up. Now we want to build that model. Again, RNNs are a little bit more involved, so we want to define these as a class. Right? We've got an input size, a hidden size, right? The output size, and the number of layers, so the number of hidden layers. Inheriting from the superclass. We've got this embedding layer. So this embedding layer says, hey, how do we go from a much higher dimensional space to a reduced dimensionality space without losing a lot of the variance? So think of like word to vec or glove models. This is the same thing. We've got a whole bunch of words. How do they relate? It's that famous king minus man equals queen kind of. Yeah. So it's using linear algebra, but it's really just a word embedding. It's a lower dimensional representation. We define the forward model. I'll skip this for now just because it could get a little bit involved, and I know we're running short on time, and you guys want to see a little bit of the things that we do. Here is where I want to make sure that we talk about what this car to tensor does, because we're not passing it, we are passing it the character itself, but under the hood it has to just have an index for that character. So under the hood it just says, it passed index 0, and then out came index so-and-so, and that's the relationship between the characters, but that's not what we're seeing. So when we pass this, this is what we're going to be sending. So if I type in, Metis 0, 1, 2, 3, ABC, Z, ABC, it says, oh yeah, 18, blah, blah, so 0, 1, 2, 3, A, B, C, Z, capital A, B, C. Right? It just does it sequentially. It's just ASCII characters. Right? So then it says, hey, when I pass in this index, and this could have been, 10,000 different words. It would have just been a bigger space, but it would have been this word is this index. For our training set, right, we're just going to say, for our training set, we're just going to take some random chunk, pass that chunk from our character to tensor, and then the target is going to be the very last thing. So we're going to take everything except the last character, and see if we can predict the last character. Okay. And then this is a little bit how we're going to evaluate that model. So we're going to try to make it come up with new phrases. Let me move that pointer there. So we're going to initialize our hidden state. Our input is going to be this prime string, right? Excuse me, right now it's just the letter A. Right? It could have been any string I want to pass, and it says, hey, take this string, pass it through our character to tensor, put it into my model, and then given what you've learned about Shakespeare and this phrase that I just passed you, generate what comes next. Right? But it's going to be a little bit different because we want it to have really some variety, so we need to have some sort of probabilistic input in here. So I'll skip this first line here, but once I have in my length, right, so as I'm still predicting new words, right, so I have a predict length of 100, I'm going to be passing this through my model and saying, okay, here's my input, here's my hidden, and then I want to make sure that I get from a multinomial distribution, because I don't always want it to say, hey, the most common thing that comes after T is H. That's the most common one, but it's not always the one. Right? I want it to give me some sort of randomness. So from this probability distribution, or in this case a multinomial distribution, pick something where this temperature is, for lack of a better word, the randomness. The higher this number is, the crazier the prediction will be. The smaller that number is, the tighter that prediction will be, and it actually tends to generate quite monotone sentences, and I'll show you in a little bit what that looks like. All right, so we go through all that and we predict. I don't think I've ran this yet. This is just the training part. I'm going to avoid this for now because I actually have these models loaded, right? So we don't have to train it. Actually, this trains for quite a while. Like I train this for like 10,000, 2,000, 3,000 epochs. It takes a very long time, especially if it's on your CPU. But I've got two models here. I've got a POTUS.PyTorch and a Shakespeare.PyTorch. So I trained text using Trump's tweets from like out into like half of 2018 or whatever, right? So, and then I trained the Shakespeare model that we've seen right now. So right now we're going to have a kind of, we want it to be a little bit sort of, giving it a little bit more diversity, which is why the temperature's a little higher. So I can pass this thing here, so I say, I'm going to give it this phrase, and I say Mueller witch hunt, and see. All right, so it does sometimes make sense, sometimes it doesn't. I think the temperature might be a little high. If we bring this a little lower, yeah. I like this one.
Sounds just like
I know. Oh, I love this. It generates clickable links. It generates random Twitter links. It is a legit clickable hyperlink that does not exist. It says Trump tends to give hyperlinks to things, and they're usually URL shortened.
Robert, it's an alternate truth.
Yeah. So I've actually, I passed my dissertation, which was written in LaTeX. I don't have it here. But it actually closes equations. It says begin equation, end equation. It does aligns, right? It'll sometimes generate legit, like compilable LaTeX. It just won't make any sense. There's no actual equation there, but it actually generates these things. And then for Billy, right? Billy Shake. To be or not to be, the thing and the will and the master, and friends are a man, shall be speak to the master, and therefore into be men. Then my lord, until you have will, hear his hands, that he hear his fling, and in his.
So we know
Those are all legit words, they just don't make sense, but...
We know which original source speaks English.
Yeah, well, one speaks Old English, one speaks gibberish.
I have an academic question. You sort of gave me the idea that econometrics, we're now trying to understand counterfactuals, trying to understand when we predict something, why is it that? So if you were to capture sort of the gradient descent or so on, the information in RNN, could you conceivably try to figure out why it reaches that point? Not necessarily visualize it, but just more.
I think for me personally, language models have always been hard to define the why, because it's incredible, right? So there's actually this link right here. The unreasonable effectiveness of neural nets is where I got the inspiration for what I did today. Andre Karpathy, yeah, wrote about how we just don't get it, but it works. He actually got Linux source code and generated Linux source code using this. Yeah.
Well, what if we were using just numerical data?
Mm-hmm. If we were using numerical data, I'm not sure.
Worth trying?
Yeah, it's worth trying. I know that I mostly use RNNs for language. So.
Give me inspiration for the next project.
Yeah. I know there were a little, well, I'm happy to stay and answer questions. I don't know if they're going to kick me out though, but it was until 3 and I'm happy to stay here longer. But if you have any questions.
What about the hot stuff now? How does it differ from this? I'm talking about BERT for NLP, the adversarial network, and the variational encoders.
Yeah, so I know BERT just recently was announced, was published. I haven't read that paper yet, and I don't know enough about variational encoders. But for GANs, you're basically trying to have a cop versus robber. Like you're basically fraudster versus a person trying to catch a fraudster, right? So you're basically pulling these back and forth. GANs in general are ridiculously tough to train because it starts off with just random noise, and it takes a really long time for it to get out of that lull and go into but the GANs are going to be doing a lot more image, so this is what you see with deep fakes or whatever.
How does the loss function propagate, and like how does the backprop and forward prop goes into something that is continuously updating itself?
I don't know off the top of my head. I'd have to go dive a little bit deeper into it, but I know that it basically tunes them independently. So it says, I've trained this model, right? Now pass it to the discriminator. This just says, hey, this is fake, this is real. I try to get as good as possible, and then I take that information, pass it to the generator, do the exact same thing again, right? And that's how you're fine-tuning until you get to things where I can't sometimes even tell them. I don't know if you guys saw the latest one of the fake celebrities. They look legit. Like people that I would be like, yeah, that's a real human being. So. Yeah. Oh, I was gonna take a giant neural net. Yeah.
What's the advantage of combining CNNs with RNNs?
I don't think there's an advantage to that. I think they have different applications, right? So CNNs are really useful for like static things, like an image. It's static. It's not changing in time, which is So a CNN, I don't need to learn from the past, right? An RNN does, right? Because an RNN says, hey, what my current state is right now was modified by what happened in the past, and I need to have information from the past trickle in. For a CNN, it's just, I just have this image, right? I'm trying to get the nuance of this image, but it's not changing in time. It's not evolving.
But people stack CNNs on top of RNNs?
If they do, I personally never done it. So. Yeah, it might be to track objects in time, or to kind of the combination of tracking an image over time, which would probably require an RNN.
Classifying an image then classify the image and put out captions.
Thanks, Robert. Thank you.